able to at least be able to have a physical model or a mathematical model of these terms. So in this case, we're going to look at these different loading conditions and see if we can write them into a 3x3 stress tensor. How about that? So we have the first case, uniaxial compression. Now, don't be confused with the stress tensor and the principal stress. So if you're looking at a uniaxial compression, so this one, the location within your stress tensor will depend pretty much on your axes. So in this case, if I have this one to be 1 and 2, then I would definitely have my compression to be here. So this one will be sigma 2, 2. Yes? And all the others are 0. Uniaxial compression. So just one normal. So what if you're going to write this one in terms of principal stress? So this one will already be your, because it's compression, it's minimum, so it's negative. If it's tension, it's positive. If it's compression, it's negative. So if you're going to write this one in terms of a principal stress, so this one is sigma ij. Okay? So I'm going to write this one in terms of the principal stress. So where will it be? Only 1, 2, 3. Upper diagonal, lower. Lower because it's negative. We know it's negative because it's compression. Okay? So here will be your, that value, sigma 2, 2 is equal to sigma 3. So this will be your sigma 3 and all the others are 0. Uniaxial compression. Beam bending, well, we've done this one already. Yes, we've done the beam bending. Yeah, if we're going to write it in a 2x2 matrix, what will happen? So we have here, if you look at this one, your beam bending, you will have this one here, sigma 1, 1. And then you have your shear stresses here, sigma 1, 2. Yes? So sigma 2, 2 is 0. So if you're going to write this one in a 2x2 matrix, your sigma ij will be sigma 1, 1, sigma 1, 2, sigma 1, 2, and 0. If you're going to write it in a 3x3 matrix, of course it's sigma 1, 1, sigma 1, 2, 0, sigma 1, 2, 0, all the others are 0. Okay, so we've done this a lot of times about the beam bending already. Big walled pressure vessel, meaning you have 3 stresses. Sigma hook, sigma longitudinal, and sigma radial. Sigma theta theta, sigma ZZ, and sigma RR. No shear stress. So let's move on. Let's have a look at the big walled pressure vessel. Okay, so you have a thick wall pressure vessel. What do you have? You have sigma theta theta, which is the largest. You have your sigma ZZ, and you have your sigma RR. Hook, longitudinal, radial. Okay? So radial meaning from inside going outwards, starting from the center of that cylinder or sphere. Well, as you can see, this one is also sigma 1, 1, sigma 2, 2. Oh, sorry. First principle, second principle, third principle. What about the what about the thin wall? Or if we're going to write the thin wall pressure vessel, that's sigma ij. If we're using a 2 by 2 matrix, that's simply sigma theta theta, sigma zz. But if you want to write it in a 3-dimensional space or a 3 by 3 tensor, then we have this one to be sigma theta theta, sigma zz, and your radial stress will be 0. Okay? Thin walled pressure vessel. Well, hydrostatic stress is quite straightforward, so that's simply sigma h all throughout. So that's sigma h. We know how to calculate this one already. So that's a diagonal matrix. Shaft impure torsion. Have a shaft impure torsion. Okay? So it's just pure shear, no normal. So if you're looking at this element here, so you have your shear stress there. No normal. So if you're going to write this one in a 2 by 2 matrix, so you have now sigma ij, you have sigma 1, 2, sigma 1, 2, 0, 0. If you write this one in a 3 by 3 matrix, all the other stresses are 0, only sigma 1, 2 is present. No sigma 1, 3, because if you're looking at this one, there's no torsion moving the shaft here. So if you have the shaft, so unless there will be a torsion or a torque trying to rotate that or twist this one, then that will be 0. So it's only this part that's going to twist this shaft here. So you only have sigma 1, 2, sigma 1, 2. All the other shear stresses are 0. Well, thin plate. Okay, what do you have for a thin plate? For thin plate. So here we assume that sigma 33 is equal to 0 because it's a thin plate. So one dimension is much smaller than the other. Okay? So assuming that's 1, that's 2. So your sigma 33 will be equal to 0. And all the other shear stresses related to that third axis will also be 0. So if you're going to write this one in, or using a 3 by 3 matrix, so that's sigma 1, 1, plane strain, so this one is a plane stress. For plane strain, you will have a sigma 33. This 4 other parameters are 0 if you're looking at the plane strain assumption. Okay, so this one is plane stress. Okay, what's the last one? Equibiaxial tension. I think you have this one in your notes, so I just took the terms in your notes. So what will be this one here? Equibiaxial tension. Meaning that the tension on one side is equal to the other side. No more load along this axis here, pointing perpendicular to this surface. So what do you get for equibiaxial tension? Sigma 11, sigma 22, all the others are 0, but sigma 11 is equal to sigma 22. Equibiaxial, equal. So sigma 11, sigma 11, all the others are 0. So here, sigma 11, sigma 11 equal to sigma 22. Okay? So, I think we learned a few more vocabularies there. Look at questions 3 and 4 now. Please proceed.